Hey guys, this is the TA for this summer. I'm going to start the new video today. So this is the Porsches and this is the lap 6. And today we are going to discuss about the different type of the Porsches and their representation in the free body diagram. Before I discuss about the free body diagram, let's talk about the force. Force is a vector quantity and the net force acting in an object is given by mass times acceleration. This is Newton's second law, right? So I think you are familiar with the acceleration in your previous lab. The acceleration is also a vector quantity that has both magnitude and direction. And the acceleration is given by the change in the velocity vector. Okay, so the net force acting in an object is given by Newton's second law, and we can use this equation in a free body diagram to find out the net force acting in an object. So let's come back to the free body diagram. The free body diagram is the is the schematic representation of the different type of the forces acting in an object. For example, the weight, normal force, frictional force, and the tension. This type of forces are included in the free body diagram. These are actually the contact forces. So those forces that act when the objects are in contact with each other. And the non-contact force, for example, the magnetic force, electric force, are not included in the free body diagram. So I'm going to discuss about some situation, and I'll draw the free body diagram, and I'll discuss the different type of the forces. I'll resolve the horizontal and the vertical components of the force, and try to figure out what physics is behind those horizontal and vertical components. Okay, let's start with some simple situation. The situation is I'm just considering a flat horizontal surface. This is my flat horizontal surface, and this is my object. Let's suppose this is a box on a flat horizontal surface. And what are the forces acting on this box? So actually there are two different forces acting in the box. Along the horizontal direction, along this side, there is no any forces acting there. But along the vertical side, along the y-axis, there are two forces. One is the weight that is acting downward, and another is the normal force. The normal force on the duster, normal force on this box due to this flat paper. Okay, so let's draw in a free body diagram. This is my flat horizontal surface. The box is resting on the flat horizontal surface. Okay, so the weight that is acting vertically downward, I could write down W, and the normal force is on the box due to the paper, and that is acting vertically upward. Okay, so this is the normal force, and we should use the proper notation to represent the different type of the forces. The weight is acting downward, but the weight of the box, B for the box, due to the earth, due to the gravity of the earth. So we write down WBE, and the normal force is normal force on the box due to the surface. Okay, so normal force on the box due to the surface. So these are the vector quantities. So I write down vector notation for both normal force and the weight. Okay, along the horizontal direction, there are no any forces acting. Now let's look at this free body diagram. This is the free body diagram. Now we know there is no net force acting on the surface on the horizontal direction and also in the vertical direction, because the system is in equilibrium. Okay, so therefore we write down the summation of the force along the y direction should be equal to 0, because there is no net force acting along the y direction. Okay, so that should be given by normal force along the y direction minus the weight of the object. Okay, why we should take minus sign? Because the upward force is taken as positive and the downward force is taken as negative. Okay, so the force are the vector quantities, and this will give you the normal force should be equal to the weight of the object. Okay, so the normal force and weight are balanced to each other. So this is the trivial case where the normal force and weight are balanced to each other. When you place an object on a flat horizontal surface, the normal force and weight are balanced to each other. And what about the horizontal direction? There are no net force acting along the horizontal direction, and you are not applying any force along the horizontal direction. So along the vertical direction, those two forces are balanced to each other. But you won't notice the same situation. You will not see the normal force and weight balancing to each other, even if the surface is flat and horizontal. I'll show in the next example. Okay. So let's look at another situation now. Now you have applied force towards the right. Okay. The same box that is placed on a horizontal surface. You have applied a force towards the right. This is the force you have applied. Okay. And what are the different forces acting on this box in the free body diagram? So the same forces, the weight is acting downward, that we write down WB as in the previous example. And there is the normal force that is going upward, normal force on the box due to the surface, so that is going upward. And you have applied one force. This is the force you have applied, and force is applied on the box. I write down BA, force applied on the box. And what about the another force? The another force is the frictional force, right? That is always opposite to the direction of the force you have applied. Okay. So this is the direction of the frictional force. I write down small f, or the frictional force on the box due to the surface. Okay. So this is the frictional force. Now let's suppose that you have applied the force in such a way that the box doesn't move, but you are still applying the force. Okay. So there is no any motion of the box, and still there is the frictional force acting towards the left. If you look at this free body diagram, the box is in equilibrium. There is no any lifting of the box. The box is not lifted towards the vertical direction. It is not moving towards the left and right of the horizontal direction. That means the system is in equilibrium. Okay. So you can look at the horizontal and vertical components of the force. Along the vertical direction, the sum of the vertical forces, okay, sum of the vertical forces should be equal to 0. Okay. So which are the vertical forces here? The same forces as we have discussed before, the normal force and weight in the vertical y direction. Okay. So normal force acting on a box, and another force is a weight that is acting downward. So these vertical forces should go to 0. Okay. And this will simply give you the normal force and the weight are equal to each other. And what about the another force along the horizontal direction? So the force along the horizontal direction is given by the sum of the forces is FBA that is going towards the right, that is taken as positive, and the frictional force that is going towards the left, that is taken as negative. And the sum of these two forces should go to 0. So this will give you the normal force and weight are balanced to each other. These two forces are balanced to each other, and these two forces are balanced to each other. Okay. So one question for you: is this the friction force static friction or kinetic friction? So this is the static friction. Okay. So this is the static frictional force. So this is the static frictional force because the object is not moving and the object is not sliding against this flat surface. Okay. So static means the system is in rest. Okay. So for example, if you apply 10 Newton of the force to the system, to the box, and the box doesn't move, so your static frictional force will be 10 Newton. If you apply 20 Newton of the force to the system and the box doesn't move, then your static frictional force will be 20 Newton. But if you apply, for example, 30 Newton of the force and the box starts to move, at that time the kinetic friction takes over. you are not going to consider the static friction. Okay, so in that case, you should consider the kinetic friction. So the static friction is simply given by the static frictional force is given by the inequality sign. This is less than or equal to coefficient of the static friction times the normal force, this normal force. Okay. So to find out the coefficient of the friction, you should consider the frictional force and the normal force. That will give you the coefficient of the static friction. Okay. So we'll discuss about the kinetic friction in the next example. So let's consider another case. Now I'm going to consider a third case where there is the same horizontal box, horizontal surface, and there is the box that is resting on the surface. Now in this case, you are pulling the box through a rope by applying the tensor force, and this box is applying the tension force on the rope due to the box. You can write down TRB, and there is one more force towards the left. What this force is called the frictional force. There is the frictional force towards the left because your box is moving towards the right. That's why the frictional force will be acting towards the left. You will still write down small f for the frictional force. Frictional force on the box due to the surface. Okay, and the same normal force and weight. The weight is going down, and the normal force is going up. Okay, so you are applying the tension force through the rope by making some angle with the horizontal direction. Let's suppose you are making angle theta. So now you should resolve this tension force along the vertical and the horizontal direction. Okay, since it is the vector quantity, you can always resolve a vector quantity. So this vector is along the y direction is, let's suppose this will be ty. Along the x direction, this will be tx. Okay, this same TRV is resolved into ty and tx. So now let's look at the horizontal and vertical components one by one. So let's suppose the box is moving with the constant velocity. If the box is moving with the constant velocity, the sum of the horizontal force and the sum of the vertical force should go to 0 separately. Okay. So if you look at the horizontal force, the sum of the horizontal force should be equal to Tx, horizontal component of the tension, minus Fps, that should go to 0. Okay? And if you look at the vertical component of the force, there are three vertical forces. One is the normal force, another is the y component of the tension force, and another is the weight that is going down. Okay? So there are three different forces. So you can write down NBS plus Ty minus WBA, and that should also go to 0 because the system is in equilibrium. If it is moving with the constant velocity, the acceleration is 0. No net force acting along the y direction, also in the x direction. So we are interested in this y component. So let's look at the y component now. Now if you consider the y component, NBS plus Ty should be equal to WBA. Okay? So it shows that the normal force and weight are not balanced to each other. Okay? So the normal force is always less than the weight. But in the previous example, we see that the normal force and weight are equal to each other. So we see that if you apply the tension force by making certain angle for the box placed in the horizontal flat surface, the normal force and weight are not balanced to each other. Okay? So this is the next situation. So you can look at the kinetic friction. So Fps is the kinetic friction because the box is moving with the constant velocity, and you can find out the kinetic friction by looking at Fps equals coefficient of the kinetic friction times the normal force, and this coefficient of the kinetic friction, this is the coefficient of the kinetic friction. This can be calculated simply by taking the ratio with the friction force and the normal force. Okay, so mu k is the ratio of the frictional force to the normal force. Okay, so in this lab today we have discussed about the different type of the contact force that can be represented in the free body diagram. You cannot represent non-contact force, for example, magnetic force in the free body diagram. I have discussed about the three different situations of the free body diagram, and I draw the free body diagram separately. The first free body diagram shows that when the box is placed in a flat horizontal surface, the normal force and the weight are balanced to each other, and that is the trivial case, and that doesn't happen always. And in the third example, when you go to the another example where you pull the box, the same box, by applying the tension force by making some angle, in that situation the normal force and the weight are not balanced to each other. Okay, and we have also discussed about the static and the kinetic friction. The static friction is acting when the object is at rest, and the kinetic friction is acting when the object is in motion. And you can find out the coefficient of the kinetic friction by taking simply the ratio between the friction force and the normal force. I think this material will be helpful for the lab next week. If you have any questions, any concern, please contact me. My email address mahat1s@nmsu.edu. Thank you for your time. Have a good day.